So today we're going to look at properties of exponents. We're going to bring back stretches, shrinks, reflections, and translation. So our moving things graphically come back into play. Okay. Let's just do it. Let's start with an example. So we're going to figure out what different things do. So if I told you we started with this function right here, y equals 2 to the x. It's an exponential function, right? Let's graph it. So let's make our table. So I'm going to pick my typical points, and we're going to figure out what this thing looks like. Okay? This kind of review for yesterday as well. So let's put the -2 in there. Flip it, so that makes that into 1/2 squared. Well, what's 1/2 squared? 1/4. And then we do the same thing with the -1 there. Got a negative in the exponent. What do we do? So it's 1/2 to the first power, which is just 1/2. 2 to the 0? 1. 2 to the first power? 2. 2 to the second power? 4. So, can we plot that? Can we graph that and see what it looks like? Okay, so let's do it. Actually, I don't want to use that one. To use this. Hopefully kids on the trip took some graph paper. Okay. So at -2, we were at 1/4, so that's like right down there. And the -1 was 1/2. 0 was 1, 1 was 2, 2 was 4. Oopsies. Are we good with that one? So the question we're going to ask ourselves is, what happens if I give it an a value? Right now we have an a value of 1. So this is just bx. We don't have the a. So what if we all of a sudden then say, okay, I'm going to mix it up here. We're going to make the spice of life. Really helps us out. We're going to look at 3 times 2 to the x. We're going to give you a different a value. So let's make a table again. Yes. Now, I've already figured out what 2 to the x is, given those x values, yes? So what do I need to do to figure out with the 3 here? Multiply by 3. So I know that 2 to the -2 is 1/4. But now I need to multiply it by that 3. So what's 3 times 1/4? 3/4. Okay, same 2 to the x. I know what 2 to the x is, but what do I got to multiply it by? 3. So that's going to be 3/2, which is 1/2. You guys see what I'm doing? Yeah. And then I know what 2 to the 0 is 1, but what do I got to multiply it by? 3. Multiply by 3. And multiply by 3. 12. So did the x values change at all? No, we didn't shift it left or right. What did we do to it? Say it again, Nate. We vertically stretched it. It's like we took it, went whoop, and pulled it up, made it stretcher, like taffy or something. Okay. So instead of being at -2 1/4, we're at -2 3/4. That's 1/2. That's at 3. That's at 6, 7, 8, 9, 10, 11, 12. That's up here at 12. So, it looks like that. And so all we're doing is just transformations that we have done in the past. The transformations work the exact same way. Okay? So to summarize that kind of a little bit. Well, let's do another one. Here we go. Let's say we're going to be crazy pants. Completely insane. You ready for this? Okay. What if I want -1/2 times 2 to the x? Craziness. What happens? What's the negative going to do? The negative reflects over the x-axis, and instead of a shrink, because the number is less than 1, it's going to be a vertical shrink by a factor of 1/2. Let's try it out. Let's do this. Okay. Vertical shrink. Oh. This is what I wrote. That's okay. I'm not feeling very good today, so I'm kind of like, who knows what I'm saying, really. It could be make no sense whatsoever. I could be speaking gibberish. Who knows, you know? I'm really tired. I'm not feeling very good, so bear with me. I'm going to use the same values that we just got done doing. Okay? So here's my 2 to the x, but now we're going to multiply it by a -1/2. So instead of being at 1/4, it's going to be at a -1/8. Instead of being at 1/2, we got to multiply it by -1/2. So it's going to be at a -1/4. What's 1 times a -1/2? -1/2. What's 2 times a -1/2? -1. What's 4 times a -1/2? -2. Are we good there? So let's graph that one and see what the heck happens, shall we? So at -2, I mean, like, we are like so close to the x-axis it almost hurts. But we're on the other side of it now, right? Because the negative reflected it. And then at -1, we're at -1/4. 0, we're at -1/2. 1, we're at -1. And 2, we're at -2. So it's getting exponential, but it's just a lot slower. It looks like that. So, graphical transformations, once again, come back into play. Okay. So let's formalize this, shall we? Okay. So, for our transformations, once again, that's the most we can really do to it. Well, plus what the negative is a reflection, okay? The A. 2 cases. If A is greater than 1, that's a vertical stretch. If A is less than 1, that's a vertical shrink. But we have seen these before, just with different functions. But they do the exact same thing. The H, that's the horizontal translation. In other words, that's the left or right. And what do we know about the thing in here? It's always the opposite of what it looks like, right? When it's done up there with the X. It's, yeah, so if this was -3, we'd actually go to the right 3. Just, we'll do examples, don't worry. And then what's the K on the back end do? This is the vertical translation, which means up and down. And the negative is the reflection. And we will do examples. I'm just letting you guys get this copied down. Do you guys have this written down? Can I move it? Oh, still got a couple. Okay. Oh, you don't want that. Or that. There we go. So here we go. Let's do one. I guess I didn't formally say the other one was an example. We'll call this example 1 then. Okay. If you called it example 1, just call it example 2. It doesn't really matter. So let's look at this. Y equals 2 to the x minus 4. So what's the minus 4 going to do to the parent function of this? What's going to happen?
Move it to the right 4.
It's going to move to right 4 units.
Is it pretty much always going to be a 2?
No. I'm kind of sticking with the 2 because then we don't have to keep remaking the table. We know what the table is for 2 to the x. Basically, I'm getting where I don't want to have to sit there and reevaluate. Do you want me to do a different one other than 2? Works the same. Okay. So if we were looking at just the parent function of 2 to the x, we've written this table down a couple times today, yes?
Yeah.
So this is 1/4, this is 1/2, 1, 2, and 4. So if we plot the parent function, easy to move. So let's plot the parent function. Okay, so here we go. So the parent function, we've also plotted this a couple times today already, so. Can you guys see that okay? This is my parent function. I'm kind of dashing it in for you. Okay, so there's the parent function. And the minus 4 up in the top tells me to shift everything to the right 4. So I'm just going to take those 5 points that I've already plotted, and I'm just going to move them over 4. Okay? So instead of being over here at -2, I'm going to go over 1, 2, 3, 4. This one, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So you just take those points, go to the right 4, and then draw your line. Or your curve, I mean. And beautiful. There it is. What do you think? Is that okay? Kind of just redoing the same stuff we've done before. Yes.
I know it's like that, but like when you plug in the x value that's there,
Mhm.
that being -6 in the x or up in the exponent, and then if you did that,
But I didn't.
would it change?
But I didn't plot way over here at -2,
So this would be the first one? Yeah, this is the parent one.
which would be like -1/64 at -2. If you put in 2, when x is 2, that'd be 2 to the -2, which is a quarter, which is what I plotted.
Oh, you changed it.
You moved it over 4. So you got to look at the new point where you're at.
Oh, so you changed the x value that you put in by 4.
Yeah, but without actually having to do it. Is that okay? Okay. It's like cheating almost, but not really.
The second graph is at 1/64 in the same spot as the first.
Yeah, so that means instead of this point being at a quarter,
Oh,
at -2, it's at 1/64,
yeah.
which is like ridiculously small.
That's what I was thinking.
Oh,
Was that same?
it's not. At -2, it's no longer the same because we moved it. Is that okay? Good. Cleared it up. I like it. So let's do another one. Here, we're going to mix it up on you. So, let's talk about this. The parent function is this guy right here. So our parent function is 1/2 to the x. I'm not 100% sure what that looks like right now in my head. So let's figure out what the parent function looks like, shall we?
I think we already have the table.
Hmm?
We already have the table for that one.
Oh, I don't know. I'm gonna do it again. My papers are all a mess over here. I think we do, but that's okay. So let's do this. So we're doing just the parent function right now. Just this guy, okay? So put the -2 in. So you gotta flip it, so that makes that 2 squared, which is 4. So put the 1/2 with the -1. The negative tells me to flip it. So it's 2. Anything to the 0 is 1. Put a 1 in. 1/2. And now put a 2 in. 1/4. So it's actually just reverse order of our other one. It's going down instead of going up, which that's what the fractional part does. So let's make a sketch of that. What are we going to have to multiply this by? 20? Oof. I'm going to have to count by something. I'm not going to have enough paper. So, let's be problem solvers, shall we? Let's change number. What happens if let's do the 20 of this, because I got to graph this, and this is going to be a pain in the butt. So let's figure out what 20 times that is. So what's 20 times 4?
80.
Oh, Lordy. Here we go, people. You ready for this? I don't know. What is it, 80? What's 20 times 2? 20 times 1? I was already over here. That's 10 and 5. So what should we probably count by? 10s or 5s? 5s or 10s. Either way, totally fine. I'm gonna count by 10s, but or by 5s, but I'm only gonna label the 10s. Is that okay? This is craziness. I love it. It is a big stretch. That is a big vertical stretch. So at -2, we're all the way up at... We're all the way up here. Crazy. And at -1, where were we? 40? Holy cow. Ha ha ha. Then we went to 20.
You're fine.
10, and then 5. Look at that crazy graph. That is crazy. It's all woo. And then it goes like, oh, bam, just joking. Okay. It's like, oh, I'm going to cross. Not really. Ha ha ha. Played a joke on you. All right. So we've done the vertical stretch. Now what's the plus 10 on the back end do?
Move it up.
Moves all our points up 10. So instead of being here at 80, it's going to be at 90. And then at 50. Oh, Miss White. Miss White miscounted. It happens. So basically it just got moved up 10. And something this steep, it's going to be kind of hard to tell, really. It's okay. Seems pretty straightforward. Yes? Okay. The last thing in this part we're going to do is on our calculator. So you need a calculator. So, for example 3, they give us some experimental data, and we need to figure out how long does it take before we can actually have a cup of coffee. Why not? I don't know. But here we go. So, what we need to do is we need to enter this into our list so we can make a scatter plot of it. So, we've done this, but at least I think we've done it. But it's been a while. So to get to there, we need to hit stat, which is right there, right below the delete button, and edit. And if you have stuff listed in list 1 and list 2, if you go up to list 1 and hit clear enter, it will clear your list. The same thing with list 2. Are we all at this screen?
Yeah.
So stat, edit, you should be here, yes? So in the first list, we need to enter in our times. So we need to enter in 0, 5, 10, 15, 20, 25, and 30. And then in list 2, the temperatures. And your lists should match at the bottom. If they don't match, we have a boo-boo. Why would you do that? So let's look at this information. So how do we turn on our stat plot? Second y equals, which is stat plot. And then turn it on. And we're in list 1, list 2, right? And before we graph, we need to talk about we gotta think about our window. Okay? So stat plot should be on, should be a dot. List 1, list 2 is where we have our information. So if we click window, what was our smallest time? Our smallest time was 0. And our biggest was 30. So if I went from -5 to like 40, is that big enough to see all those values in the x's?
Yeah.
And then for the y's, what should our small y be? Let's make it 0. And what's our biggest? 203. I like to go bigger, so I'm going to go 250. Okay, let's see. Oh, I don't want that in there. I do that all the time when I do a stat plot. I forget to hit y equal. I don't want that equation. So you just clear it. Is that okay? So just clear it because it's silliness. We don't need it. So does that look like an exponential graph?
Yeah.
Yeah. Super awesome. So exponential is a good thing for us to do. What I would like you to do is we're going to have the calculator tell us the exponential model we're going to use. Okay? We don't have to figure it out. We're going to have the calculator tell us. So if you hit stat and go over to calculate, we're going to use an exponential regression. Oh, there it is. So EXP is exponential. So we want it to use this information. Okay? So when we go here, we also, so what does it automatically assume which two lists? List 1 and list 2, and that's where we're in, so we don't have to change that. But I want it to also put the equation into y1. So remember how we get there? So hit vars, y vars, function, y1. So vars, which is right by clear, go over to y vars. We're in function mode, and I want it in y1. And then hit enter. Some of you guys probably have R's, which I kind of want. We've turned these on before. If it's off, I'll... The closer it is to 1 or -1, the better the fit.
Yeah.
We have a pretty good fit. Yes.
Since it's a scatter plot.
Yeah.
Wait, what do you do after the y1 is done?
Hit enter. And it should do something and then spit out some numbers. Yeah? Okay. So I'm going to write down my little equation here so I do not forget him. So your equation should be 196.66 times, and your b is 0.9798 to the x. You just take these values here and put that in for a and put that in for b, right? And what do we want to know? I forgot what we want to know. For it to, till we can drink it?
185.
185. So because I threw that into y1 right here, so for y2, what are we gonna do?
How'd you get that in there?
Remember when I went the y1 thing?
It's already there.
It just puts it in for you. You don't even have to think about it. 185. And do we need the plot on anymore? No. So if you just go up, see where it's highlighting plot 1, and you hit enter, it will turn it off. You don't have no more plot 1. I don't need it anymore. I used it. I used it for what I wanted, and then I let it go. So now we need to figure out where these two things cross, right? Mm-hmm. Oh, it's a beautiful exponential function. Oh, there it is. Can we find that intersection?
Yes, we can.
Second, calculate. Number 5. Is that the first curve? Yep. Is that the second curve? Yep. And scroll on over to the guess.
How do you get that line on
2.7 minutes.
Oh, the y, that was y in y2. I put 185 because they said that's when it cools off to when we can drink it.
I got it. I did that too.
So you put y1 in there,
Yeah.
and then in y2 you have 185.
Yeah. I'm like, you know how you have that like line graph line? Yeah, I don't have that.
The curve or the straight line?
The straight line. Like,
Bring me your calculator, please. Oh, poop. How many minutes?
one
About 2.7?
straight down.
Oh, that's your coordinate, your axes. Because you turn it off for your stats class, I bet you.
That's
So-
his computer, so, or I mean his calculator.
So what you got to do is second format,
Mm-hmm.
and then change it to axes on,
Oh, okay.
and then there you go.
Okay, I like that so much.
Is that okay?
Yeah, thank you.
You're welcome. Are we okay with the regression lines and all that good stuff? Okay. Okay. On to part 2, because I think it's really not that long. Now, you sometimes will get different answers than the book gets because we made the calculator put the equation in there. So we carried the decimal out really, really far, where the book rounds it. So there is some rounding error, but if you just have the calculator keep those decimals, you're going to get a little bit different answer than the back of the book gets if you check. It's okay. As long as you're kind of close, assume it's a rounding error because of the decimals. Okay?
So half a minute could burn your mouth.
What?
The difference of half a minute between the rounding and not rounding could burn your mouth.
I know. Could be bad. Could end poorly. Okay. So the last thing we're gonna do is in nature, exponential things happen naturally. You guys have seen the spirals that you can get off of a sunflower, right? Have you guys seen the picture of a sunflower and they put a spiral in there? No? Yeah, really cool. Archimedeal spiral. It's actually part of the golden ratio, which is aesthetically... We're going to watch Donald Duck and Math Magic Line at some point because it's in there. I have to show you. I'll show you tomorrow.
Saw a little bit of it. It's on the front of the geometry book.
It's on the front of the geometry book. It's got that cactus on there. I'll queue up that part on the Donald Duck and Math Magic Land for you guys tomorrow, okay? Oh, bummer. So, these things naturally occur in nature. And there's one very special one, and it's e to the x. This is the exponential function, e to the x. We say that this has a base e. If on your calculator, if you look right here, there's an ln button. You guys see the ln button right by the 4? If you go second ln and then put a 1 there, so it should be e to the first power, you actually get a number out. E represents this number, 2.71828, etc., etc. This is like pi. It's an irrational number. It doesn't end. It never repeats.
Isn't that Euler's numbers?
I don't know about that. I'd have to look that up. I don't remember. It could be. I just don't know. Sometimes this is referred to as the natural base because it happens in nature all the time. So a lot of times it'll be called the natural base. Okay? So we're going to learn all about this guy right now today. Okay? Another way we look at these are continuous growth or decay. In the perfect world, you would love to have E as your base if you're looking into interest rates where you were getting money, because it's compounding all the time. It's continuously compounding versus like in the bank, sometimes when you get a rate, they'll say we'll compound it monthly. So you only get extra money every month. Where if your base was E, which banks will probably never ever do because that would be the silliest thing they could. If you had base E, that means you're always getting money back from the bank. You're always getting interest. So all of a sudden your money grows like crazy. And banks are like, what happened? And they're crying. So they don't use base E because they would lose a lot of money. Okay, so they use different bases. Base E, continuously compounding. You're always getting some money from these people. I would love it if they use base E.
You should sneak in and change it.
They know about radioactive decay from science.
Oh, radioactive decay? You guys know radioactive decay from science class?
Sure, I'm glad.
Sure. They gave me, yeah, sure. I know. I know. They're like, they mention it. That's okay. I'm not worried. I'm not worried. Okay, so we have so e to the first power, this is what that number represents, right? Let's look at this graphically on our calculator. So let's hit y equals, please. Clear these guys out. I don't want these in here anymore. I hate this calculator. I want to know what e to the x looks like. So where's the e button again? Second ln, good. And we want it to the x. So e to the x. That's what we want to look at. And we just graphed a plot function, so our window is all sorts of crazy. Right? So, let's zoom 6 it. Beautiful. Does that look like an exponential function? Yeah, looks like the ones we've been looking at, right? Okay. What if I asked you to figure out what e to the third was? What would you do? So second ln and then put a 3. That's the value of e to the third. Yeah, cool. That's that. Okay. Oh! Did you zoom 6 it? Did you go e to the x? Did you do e to the x?
No, yeah, I did that.
In the y equals?
Yeah.
Then I'll have to look at it later. I can come check your calculator out later. The really only thing from part 2 that we're going to look at today, other than talking about a natural base, is compounding continuously, which we just were talking about. Continuously compounded interest. Continually compounded interest, this is the base E. Have you ever heard of anybody ever say apert? Oh, well, you haven't lived. Okay. You're welcome. I just spiced up your life. The A is the amount that we want to have, or the amount that we get. Okay. P is the principal. It's what we start with. We talked about principal the other day. It's what you start with. And now, what we talked, remember when we had the 1 plus r raised to the x? Right? Where this was the base? Our base is now e, but r, the rate, all of a sudden got sucked up into the exponent. This is your rate as a percentage rate, but we have to use it as a decimal. And t is time.
What does that first thing say? Amount? Or what is it?
Amount.
Oh, amount.
And time is measured in years.
Is it always years?
Yes.
It's the 1 plus r.
This is what we did yesterday. And I'm just saying, instead of 1 plus r as our base, e is our base. And our rate goes up here. Okay? So that was from yesterday. Your start with. What you start with.
This is what they use for interest.
This is what you wish banks used for interest.
Do they use different?
Yeah, they use this one. Don't worry about the N. And it's just how many times a year they compound it. And so usually your interest rate is small, and usually they don't compound it very often, so you're not getting much interest from the bank. You wish they used that when you needed to get paid, but you would hate it if you had to pay back. Because if you're like, if I owed you $20, but we're compounding continuously, and it takes me like a year, ridiculous how much more I'm gonna owe you. I don't even want to start with it. I would be really sad.
Credit cards compound every day.
Yep.
They're
So credit cards use that?
Huh?
Credit cards use that?
That's how they get you, with the interest rates and the interest that you owe them. And that's why when you have a credit card, you want to pay them back quickly, because you're the interest is going to kill you. And the minimum payment usually sometimes barely even covers the interest, if it does at all, depending on how big your credit card is. So if you're not even paying off the interest that you owe them, you're never going to get that balance down to where you're not going to owe them anymore. And that's how people get into credit card debt.
Mr.
It's-
Merrick showed us a really scary video on that.
Mm-hmm.
They are so mean.
Mm-hmm.
Credit card companies.
Mhm.
You need like at least 3 of them to have a good FICO score.
Isn't that, it's crazy.
That's stupid.
Yeah.
They tell you like, oh, like this is like the least you can pay, and they'll go down, and it's like if you pay like the least amount of payment, you'll be paying it off for 30 years.
Yeah.
For just like one trip to the grocery store.
Yeah. Yeah.
Well, and that's why when you call, like, if you're ready to pay it off, you call the credit card company, say, I'd like to know my balance. They read you the balance. You go, write the check, put it in the mail, and it takes 3 days to get there, and you haven't paid it off. Because they accrued interest for 3 days while your check was in transit. And so you still owe, I mean, it's probably not much, but you still owe money, like, you still didn't pay it off.
So
Then
so like basically you need to send it like 6 days early instead of 3 days.
Yeah, yeah. Well, and just know that you're gonna get a balance statement that says you still owe them $4. Like, oh, for crying out loud. So,
So it's all about exponential functions, people. That's where the money world lives. It's all about this kind of stuff. It's craziness. Are we ready to do this example and we'll be good? Okay. Have we scared you yet? We didn't mean to, sorry. So the last example we're gonna do today, I have no idea what example. I'm making these up. I don't even know. Example whatever. Okay. Suppose you won a contest at the start of 5th grade that deposited $3,000 into an account that pays 5% annual interest compounded continuously. How much will you have 4 years later? So when they tell you you won pay attention please, ladies. When they tell you you won $3,000, what are we going to put that in for? The P, it's the principal, it's what we started with. So the amount we get, we started with $3,000. And it said compounded continuously, so my base is E. Raised to, you got to change this to a decimal, so 0.05 times
3,000 was P, not A.
P, wherever I put it. And T is my 4. Right? So A is, this is how we're going to figure out how much money we're going to make. No, we don't have to do this by hand. Hallelujah. Just put in your calculator and go, okay? So in your calculator, oops, it's already off. I know I have low batteries. There you go, 3,000. Second E, and then if you put parentheses, 0.05 times 4. Yeah? How much money did you make in 4 years? 664. Good call. We have a total of 3,664, but 3,000 is what we...
Please come to the office. Juan Rodriguez, please come to the office now. Thank you.
But the 3,000 we started with. So how much did we make? 664. How much we have in the account? 3,664. Are there questions? Are we feeling okay with this? The first part was transformations. Second part was all about the natural base. Okay? And for your homework, I gave you odds, so you can check your answer in the back. Well, one of them I gave you all, but here you go. So part 1, page 474, questions 7 through 19 odd, 23 and 25. Part 2, page 478. Let me make sure I still like this. Yes, I do. Not that bad.